This is a review for an exam. This is part two of the review, and not only is it a review, but we're working out the problems step by step. Now, I want to point out that this is not a problem that is on the exam, but similar, same type of thinking that you will need to use for one on the exam or several on the exam. This is number one. There are four in all we want to look at here today. A person opens their smartphone in a location without Wi-Fi and begins using up cellular data. Let D of T, capital D of T, represents the total amount of cellular data in megabytes the smartphone has used after T hours. And they want us to explain, what does D prime of 3 equal 140 mean? Well, D prime is D prime of T is the derivative. So that's the rate of change of the data after 3 hours, and it's changing at the rate of 140 megabytes per hour at the end of 3 hours. So that's the answer that you can read here on this particular problem. It might not be clear to you what it is, but that's when you stop and think about it, that's pretty obvious, I would think. Down here, we have a second part to this problem where we told that D of 3 is 346. We're given this, and we just were given that D prime of 3 is 140. And can we find D of 3.2? Now, we've got D of 3. We want, and we've got D prime of 3 and D of 3. 3.2 is close to 3. And so what we're going to do is we want to find the D prime of 3. And so what we're going to do is find the slope of the line connecting D of 3, which is with D of 3.2, using a y2 minus y1 over x2 minus x1. So D prime of 3, which is what we want, is y2, that's D of 3.2, minus y1, which is D of 3, over x2, which is 3.2 minus x to 1, which is 3, and we just do the arithmetic. We plug in what we know, and this is what we don't know, multiply each side of the equation by 2/10. 1/10 of 140 is 14, so it's 28. We add this over, and we have our answer there. That's the megabytes. It's 3.2 hours. So that pretty much completes that particular problem. What we have on this problem here is we've got a graph here. A particle is moving along the x-axis. In other words, a particle is moving along the x-axis. It's not going up or down, it's moving along the x-axis. It goes over and goes back and forth like that. And its velocity, is given, this is the velocity curve from time 0 to time 13. Now we're told that it's differentiable. That means it's no sharp points and that it's continuous, no breaks in the graph, okay? And that's important to know. So this is the velocity curve, okay? This is the velocity curve. And we're told that the velocity, we can see at t equals 0, it's 0. At t equals 4, it's 0. At t equals 10, it's also 0, because the velocity crosses the axis here. This is not the path of the moving particle. This is the graph of its velocity. And we also see that at t equal 2, we have, this is when the tangent here is 0, the second derivative, and the second derivative here is 0. So we got that kind of out of the way. And we're told that the area is bounded by the t-axis in the graph, we were interested in the area here, here, and here. And we're told that I've labeled these here for you. This is 4, but it's under the graph, so it's -4. And this is under the graph above the x-axis, and so it's +9. And this is area here is below the x-axis, so it's -9. And the question here is, we're also told at time t equals 0, the particle is x is at -3. This is a rather cumbersome problem. In other words, it's starting on the number line at -3, which is over here. And the question here is, find both the time and position of the particle when it is farthest to the right and explain your answer. Well, from 0 to 4, it's got a negative velocity. So that means it's moving to the left, okay? To the left. Well, it starts at -3. So, and this is its distance is -4. That's the antiderivative velocity. Its distance, it's -4. So it goes from -3 to -4. Or -4, which is going to make it -3, and then moves further left, -4, puts it at -7. Now here, it's got a positive velocity, which means it's turning around, and its distance is 9, so it's going to go from this -7, 9 units to the right, puts it at 2. And then here is -9, means it's turning around again, going to the left, which means it's going to go back to -7 now. But the question is, when is it farthest to the right? Well, it starts at -3, goes to -7, goes to 2, and back to -7. So what's the most right point? And the most right point is x equals 2. B part of this question says, from 3 to 2, the speed of the particle, is it increasing or decreasing? Now, from 3 to 4, I think it's what everyone just said. Let me check that out again. From 3 to 4, now the velocity is negative, but is it increasing? What's the slope of this graph from 3 to 4, the tangent? It's uphill, it's positive. And so it's increasing at that time. And it says also in this problem, you won't know if it's increasing or decreasing. And the fact is, it's increasing. So that's the answer to that. It's because, I know I'm talking slowly about this, I'm having to think through this as I go along. We want to find out, is the velocity increasing? And the slope it's the slope of the velocity curve, which is the second derivative. And it's a positive slope there. And then they ask us on the interval from 3 to 4, is the speed of the particle, well, that's what we just answered. C part of this, during what time interval, if any, is the acceleration of the part negative? Now, acceleration, that's the second derivative. In other words, when is the slope negative? The slope of this graph, the tangent is negative from 0 to 2 and from 9 to 13. So I apologize for sounding rather fuddled, but maybe it's helpful to you if I do. But you can go back and listen to this and see if you understand what these 3 parts are talking about. The main thing you have to understand is something we had in class. We're having to address basically the distance function from the derivative. In other words, we're given the derivative and we want to discuss the original function, which is the antiderivative. And that's where, of course, the antiderivative is integration, and that happens to be area. So let's go to problem number 3. We have an ice sculpture that's melting, and it's cone shape. It maintains a cone shape the whole time it's melting. It might not seem realistic, but we don't want to complicate this. So its size is decreasing. It says the radius of the base of the cone is twice differentiable. That means we can find the first and second derivative of this, okay? Now, question A, we have a table here. This is days, day 0, day 3, day 6, day 9, day 12, and the rate, the radius is changing. It's in measures in centimeters per day. So it starts out day 0, it's changing at minus 6.3. And it's going down, it's changing at minus 5.1, then minus 4.5, and on the 12th day, it's changing at the rate of 3.6. Now, the question here, is there a time between 0 and 3 in which r prime of t is minus 6? Now, this is why it says it's twice differentiable, which means continuous. So we know that going along here, there's no break in the graph. No break. So we go from minus 6.3 to minus 5.1, and there's no break in the graph. And so there must be a value of minus 6 somewhere between here. It's something called the intermediate value theorem that applies to what's going on here. And just point that out for you of interest. But if there's no break in it, it goes from minus 6.3 to minus 5.1. Remember that minus 6 is to the right of minus 6.3, and this is further to the right. So there's got to be, by virtue of the fact that it's continuous, there's got to be a point there. And then it's asked us to use Riemann's sums with n equals 4 using the right-hand method to evaluate, in other words, integrate this. So we're going from 0 to 12. So b minus a, it's 12 minus 0, intervals of 4, so we're going up by 3s. And we're going up by 3s, but it's right-hand method, so we're not going to use 0. We'll use 3, 6, 9, and 12 as our points. So we'll find f of 3, f of 6, r of 3, r of 6, r of 9, r of 12. And we pick those values out from the graph. And that's the heights of the rectangles. We're using it, remember, the Riemann sum, right-hand method. And this is the width of each of the rectangles. So we multiply the sum by 3, and we get here that this is it should be left out here. This should be a negative 51.3 for that. And so that takes care of that problem. And that problem number 4, the population in Richmond, Virginia in 2005 was 197,998. P of t represents the population at the year t, or t with the number of years since 2005. So t of 0 would be 2005, t of 1 would be 2006, and so on. All right. And so they ask us here, what is p of 0? Well, p of 0, it means no movement, no years past have elapsed. So p of 0 is 2005. And what is p of, well, you've grown none, so it's going to be what it said it was in 2005, okay, or 197,998. Then the problem asks us to explain what it means. What's the integral of r of t? What's the integral of r of t in this particular problem? And that's going to be in context of the problem. Well, r of t is the rate of which the population is growing, changing. See, it would seem to be that maybe it would be clear if they had r prime of t as the rate, but they don't. They've called it just r of t, and that's kind of a distraction there. But the integral of r of t is the r of t is the rate at which it's growing. So the integral is the population, or p of t. So we want the from 0 to 9. So the integral of this thing is p of t from 0 to 9, which is p of 9 minus p of 0. And so that's what that stands for. Now, p of 9, by the way, is the year 2014. So this is the change in the population between 2005 and 2014. They didn't ask for an answer. We can't get an answer there. Now, part C, does P of 9 equal what we just found here? No, this is the change, or the amount of change. P of 9 is the population 9 in 2014. P of 9 is the population in 2014, but this is the population change between 214 and 205. And then it asks us to write an expression or some interval to represent the following statement: the growth in Richmond, Virginia from 2006 to 2009. Well, 2006 is 1 year after 2005, and 2009 is 4 years, and so that would be the expression we would have, and they tell us it's this. And so this is kind of it's such an easy problem once it's explained that you wonder why is it put here, but it's making you think. There's no math involved here, no calculus involved here, but just describing what is going on. So you need to listen to this video, this YouTube, several times to make sure if you were given a problem similar to this, could you handle it? And so this completes this review.